Thank you, Benny, for that introduction. So I'm now going to present our work, Clockwork Finance. So we know that DeFi has experienced a meteoric rise, handling billions of dollars. This graph is until 2022 when there was a peak, but still it's catering to hundreds of billions of dollars. And this rise of DeFi has been powered through smart contracts, which really operate like clockwork. Now, what do I mean by that? The smart contracts execute in sequential and atomic transactions. This execution is deterministic, and most blockchains have transparent execution. Therefore, this allows for easy interoperability of smart contracts and allows for novel financial instruments to be built. This has also led to something called money Legos, which means these contracts compose with each other seamlessly. But this also leads to unintended behavior. So let me give you a quick example. Suppose the user here is trading with a decentralized exchange. A miner, or now a validator, can come in and sandwich, so to speak, the user's transaction and thereby earning a profit in the process. This is called classically a sandwich attack. This class of profitable strategies by miners or validators is broadly captured by this umbrella notion of MEV, which means the validator can extract profits by reordering, censoring, or inserting new transactions. Now, this behavior is not limited to just one contract. In fact, when we compose contracts, this behavior gets even worse. For example, when we have flash loans with decentralized exchanges and many other compositions, we see a large bunch of high-profile attacks that arise precisely because of unintended behavior of smart contracts. And in fact, there is an entire industry of MEV that has sprung around this, with hundreds of millions of dollars being extracted. Now, existing techniques for security have fallen short to capture this notion. For example, the existing techniques like, say, human auditing, fuzz testing, functional correctness analysis, static analysis, all of them really focus on things like bug hunting, data leakage, and so on. But they fail to capture this economic aspect of smart contracts. So in this work, we directly reason about the economic properties of smart contracts and leverage existing formal verification techniques to reason about these properties. Note that unlike traditional finance, these contracts can be, are amenable to formal verification because their execution is deterministic, atomic, and so on. Our work has benefits to different stakeholders in the ecosystem. Developers can actually prove bounds on the MEV that can be extracted from their contracts. Users can analyze the MEV that's being extracted from their transactions. And of course, researchers can also use our tool to study the impact of MEV. Now, in the rest of this talk, I'm going to briefly touch upon the definition aspects. Believe it or not, there was not even a definition of MEV before our work. And then I'm going to talk about how we do practical instantiation of it into Clockwork Finance framework. So intuitively, consider the given state S, and a miner or a validator has some balance in the state S, and there are some contracts in the state S. If the validator produces a valid block, which increases its balance, denoted by the green bar here, the validator extracts some value in this state S. And the maximum value that it can extract from any valid block is termed as MEV. And we can generalize it to multiple players and multiple chains, enabling us to also study multi-block MEV. Now, the key thing to note here is that we can use MEV as the measure of economic security because miner is really the most powerful actor in the ecosystem, or now the validator. And MEV, in some sense, subsumes all the other economic attacks that are worthwhile. And once we have this definition of MEV, we can also talk about what it means to have secure composition of contracts. When you have a new contract C, you add it to the state S and see whether MEV has increased or not. Depending on that, you can classify whether this contract composes securely or not. I'll encourage you to look at the paper for the formalism regarding this. Now, let's get to the practical instantiation of this into Clockwork Finance framework. Before that, I'll just give a very high-level overview of formal verification. So consider this program, which is represented as this abstract tree of execution flow, starting from the initial state S. And we want to verify this blue property here, which should hold in all the end states of the program. If this property holds, then the formal verification tool should give us a proof that this property actually holds. And if this property does not hold in any one state, then it should give us a counterexample trace starting from the initial state to this final state where the property is being violated. Now, how do we take this and use it inside CFF? Well, consider that you have the initial state S and some transactions that are available. And we want to verify the property that MEV is less than some parameter delta. These transactions, note that can be symbolic, which means that these transactions can be of the form swap X amounts of ETH for Y amounts of dollars, where X and Y are some integers greater than 0. Now, the program that we analyze is basically all the reorderings of these transactions and see whether MEV is less than delta or not in the final state after executing these reorderings. The final MEV is definitely a function of the input parameters here, for example, X and Y. And if the MEV is more than delta, then you actually get a counterexample trace. In this case, the counterexample trace would be a concrete ordering of transactions. So for example, here, this concrete ordering is transaction 1, 2, 3 played on top of the state S. We use K-framework for the engine for formal verification in CFF. The thing to note here is that when you give a formal language model to the framework, it will automatically generate parsers, compilers, verifiers, symbolic executors for your language model. It also helps that the framework is human readable in terms of its specifications, and there is formal semantics of Ethereum virtual machine inside this framework. Great. So now we have these tools. We have the deductive verifier from K-framework. We give the input state and the transactions that we want to consider. And all we need to now do is specify the language model, right? So the first part of the language model is the codified Clockwork definitions. By that, I mean the definitions of MEV, the definitions of secure composition, the definitions of reordering transactions, and so on. We, of course, need the smart contract code. And we need the EVM semantics, which means how do you execute these transactions on the smart contracts. Once you specify this language model and the property of verification of MEV, you actually get either a composability proof if the property holds, or you get a counter-example strategy, which means you get concrete transaction trace, like transaction 1, 2, 3, the values of the parameters in all those transactions, and so on. Now, in this form, in practice, this cannot be instantiated in practice because this problem is intractable. So we simplify this a little bit by simplifying the smart contract code into something that we call CFF models. Now, these CFF models are obtained from smart contract code by simplifying the smart contract code such that these paths are only an over-approximation. So what I mean is when you replace the smart contract code with CFF models, the final MEV is only more than what it would have been. What this means is during our verification, we only have false positives, but we don't have any false negatives. And once you have that, you can actually weed out these false positives, as I'll discuss later. But here's an example of how we obtain CFF models. So this is a smart contract code for the Uniswap v2 contract. It has a bunch of things that we don't really need for our analysis. So for example, asserting that the deadline is more than some timestamp, asserting that some tokens are being bought more than a threshold, and so on. So we can prune out all these paths and obtain a simplified model, which is an over-approximation of the behavior of this contract. And once we have that, we can weed out the false positives by simply simulating the counterexamples that we obtain. These counterexamples are concrete traces, so you can actually simulate them on an Aragon client. We do many more scaling optimizations. I'll just quickly mention a few of them. We do some general optimizations, like, for example, you really don't need to reorder transactions from a single user because those transactions would be rejected. They need to really be ordered through their nonces. We also find that if you randomize the reorderings, so you explore them in a random order, then this leads to better convergence. And we also do some contract-specific optimizations, like there's path independence for Uniswap. So really, the reordering does not change the final state for Uniswap. This evaluation, when we wrote the paper, showed that CFF is actually practical and can, for AMMs, actually find out that there is, on average, say, 0.5 MEV per block when we did this analysis. We also do this analysis for composition of contracts. So when you compose MakerDAO with Uniswap and you slot in the Uniswap price as an oracle in MakerDAO, then how much MEV can be extracted using CFF. There are many more evaluations of CFF in our paper. I would encourage you to take a look at it. We do analysis of attacks on governance contracts, flash loans, airdrops, and so on. With that, I'm happy to take questions.
Questions?
Hi, great work and great talk. I have a question. What are the boundaries of the analysis? In a sense, like attacks could span over multiple blocks, or like, are you considering just reorderings, or also transactions that the miners might actively insert? What are the boundaries of the analysis?
Yeah, thanks for that question. So the first of all, the transactions that we analyze here, they really do not scale beyond more than a few dozen transactions. So we don't really analyze multiple blocks. Just one block is already quite a lot for the analysis. In terms of the transactions being considered, those are like the parameters of the problem. So you can input user transactions from the mempool, and you specify these templates of miner insertion. So when I mentioned swap X ETH for Y dollars, that is one template that is added to the analysis. So you'll have some manually specified templates which will be given to the analysis.
Okay, so basically the usage of the tool a little bit differs depending on whether you want to consider transactions that are already on chain, so like you want to use your tool to measure possible MAV on existing chains, or rather if you wanted to analyze a contract before you upload it on chain, because there you don't know what other contracts could do with it, so the search space might be significant.
Right, so yeah, different stakeholders will use the tool differently. So for example, if you want to only study historical transactions, you can't insert new transactions. You'll only study the existing transactions. But if you're doing it in real time, you'll basically specify some template for what insertions can be done.
Thank you.
Thank you. Let's thank the speaker again.